Hello, I'm Mr. McBrien. This is TEJ3M, Boolean Logic. The Ontario curriculum states that students will relate Boolean algebra to the fundamental logic gates and to combinations of these gates, including symbolic, algebraic, and numeric representations. That's what we're going to do today. We're going to relate Boolean algebra to the design of circuits using something called logic gates. Okay, so Boolean logic, it's been around for a while. George Boole developed it in the 1850s, and we eventually named it after him. That's not a typo. He developed Boolean logic long before computers, or even really electricity the way we look at it today. So we can use Boolean equations, though, in a different way than he intended, and look at the binary number system and use that to describe the logic of computer chips and of circuits in general. Let's back up a little and have a look at the way he looked at Boolean logic. So he had a series of operators with which he could look at populations. And fittingly, we'll look at the AND operator first. So if we want to look at the parking lot of the school, we can look out and we can see a bunch of black cars. We can see a bunch of cars that are made in Canada. And if we look at those populations, they're not exclusive. Some of them are made in Canada and are black cars. So our AND operator describes the intersection between these two populations. And incidentally, we have a special name for these diagrams. They're called Venn diagrams. So the shaded group is comprised of cars that are black and made in Canada. So the other operators work in a similar fashion, looking at the populations. And we can illustrate these again using the parking lot. So we can look at the population in the parking lot and say which ones are black cars or made in Canada. And in fact, what we see is that every car that we considered in the previous case fits our new definition. The shaded group is comprised of cars that are black or made in Canada. In other words, everything in either one or both of the circles fits our criterion. But then we can look at a different case. So we can look at a NOR designation. We can look at this whichever way we want to, but the way I like to look at it, I call this not or. So we're looking for the cars that are not black or made in Canada. The shaded group, not black or made in Canada. And so it's the exact opposite of our OR set. And one way of looking at it is saying, and maybe the best way of looking at it is saying, it's the group that are not the group that fits the OR criterion. So the binary system, we can move back to this and talk about a 1 in the binary system represents an on or a yes, and a 0 represents off or no, and we can start to think about relating Boolean logic to computer electronics. And we do this through a hardware component called a logic gate. A gate essentially is, well, a gate. It controls the flow of electricity. It takes inputs, usually called A and or B, and gives an output, usually called Y or X. And in binary logic, we'll talk about a 0 for a no and a 1 for a yes. In a positive logic circuit, an electronic circuit, the way we view it, we'll talk about 0 volts as low or no, and 5 volts as high or yes. And here's a quick summary of the gates that we have available to us, the standard gates. So we have schematics of them shown here. The gates themselves are AND, OR, NOT, NOR, XOR, NAND, or XNOR gates. And we have a Boolean equation that describes these. And you need to be able to recognize the Boolean equations as well as the operators themselves. So how do we analyze circuits and come up with a way that they work? We typically look at them on the basis of what's called truth tables. We consider all of the possible cases of inputs to the circuit or the gate, and then we detail the outputs. So this truth table approach is extremely rigorous and a very effective way to look at a given system. Okay, so we can use these truth tables to determine the outputs based on the inputs. Here's a truth table here, and I'm going to demonstrate how to work it using an AND gate. And just for fun, we're going to fire up a simulator and look at this from a simulated point of view, simulating an AND gate. Okay, so this is the logic lab where we're going to do our simulation. What we're going to do is just drag in a few components so that we can examine the behavior of an AND gate. Okay, so here are two simple switches from our input side, and we're going to get ourselves an AND gate. We're going to get ourselves, let's say, a light for output to indicate yes. And then we'll wire up our circuit. Really, this isn't very different than wiring up an electric circuit. We're simply wiring our switches up. We would, of course, if we had a real circuit, we would have a voltage that they controlled. And then it would go through our gate to our output. Now, I'd like you to please keep your truth table open as you observe the behavior of this system. It's now live. The two switches are off. Our AND gate is performing its logic and saying that if both switches are off, then our output should be no. And so what I'd like you to do on your truth table is fill in a 0 for input A, a 0 for input B, and a 0 for output. However, if we turn our input A on and indicate a 1 there, we have a new situation. The system evaluates the logic and again says if input A is a 1, input B is a 0, then the output is a 0. Let's go to our next situation. Input B is a 1, input A is a 0, and again our output is a 0. And finally, our last possibility, we flip the switch, input A is a 1, input B is a 1, and finally our system lights up. This is the case we are looking for where the output is a 1. So we've now completed our truth table for our simple system that we were considering today. Okay, hopefully you've got your table then filled out. Here's mine here for the AND gate. As we discussed, both inputs 0, our output is 0, and so on. And the only case where the output is 1 is when both inputs are 1. In other words, both inputs must be a yes to get yes as output. So let's look at the other possibilities. An OR gate. In the OR case, the the only case where we get an output of 0 is when both inputs are 0. In other words, if either input or both inputs are yes, the output is yes. A NOT gate is kind of interesting. It essentially inverts the input, and this is in fact one term for a NOT gate is an inverter. So if the input is 0, the output is 1. If the input is 1, the output's 0. So the output's the opposite of the input. For a NOR gate, we can think of this as a NOT OR gate. The only case where we get an output of 1 is when both inputs are 0. And that's the exact opposite of the OR gate. Now there's a very interesting possibility for these gates, and when we see an X, we can think of that as an exclusive designation. An XOR gate gives an output of 1 only when one of the inputs is 1, not both. So only one input can be 1 to get a 1 as an output. A NOT AND gate is the inverse of the AND gate. So the only case that gives an output of 0 is when both inputs are 1s. And an exclusive NOR gate is the inverse of an exclusive OR gate. So an XNOR gate is the inverse of an XOR gate. In other words, both inputs have to be 0 or both inputs have to be 1 in order to get an output of 1. Okay, so our activity, you have your activity sheet in front of you. What I'd like you to do is please pause the video, and I'd like you to please, on your note template, sketch the Venn diagram. So I did 3 of the Venn diagrams at the beginning. You have 7 gates. Do the Venn diagrams for the other 4 gates, please. And there's space in there on your notes template. It's a really good idea not to look them up. You won't remember much if you look them up, but if you think about it and do it yourself, you should be able to gain some knowledge. So I'd invite you to pause the video now and work on that. Work on filling in that worksheet, and we'll take it up tomorrow. Alright, so welcome back from your Venn diagram activity. Let's look at some of the utility of logic gates. They really aren't all that interesting when you look at them just on their own. But what we can do is use them in combination in circuits to accomplish things. And the good news is when a logic for a given situation is pretty simple, we don't need a computer or even a microcontroller to do our logic for us. We can use a few simple cheap logic gates instead. So let's look at a situation that's a little bit trivial in some ways. This isn't precisely the way you would do this, but it illustrates our concept very well, so I think it's worth doing. Let's imagine we're designing a burglar alarm system. We want the alarm to trigger if any of the sensors indicate entry. And so we've got a little apartment and we have sensors on 6 windows and a couple of doors, for example. We can use a series of OR gates to give a positive signal if a window or a door is penetrated. And so to say it another way, if any entrance sensor is triggered, produce a high voltage. And notice that our OR logic is very useful for this. We don't need people breaking into a door and a window in order to want our alarm to go. They only need to break in through one place to make our alarm trigger. And remember the Boolean logic that we haven't talked about too much, the nomenclature on the right hand side in that big table. Well, now we can look at it and say we can use our OR operator. And so for Boolean logic, a Boolean expression, we can say that we want the alarm to trigger, we want a positive result from our circuit if window 1 or window 2 or window 3 or window 4, window 5, window 6, or either of the doors triggers. We want the alarm to trigger. And we can look at the schematic here. We can combine our gates. First off, looking at combining, since in this case we've only got 2 input gates, there are other gates available, but we can use these to illustrate our point. Our initial set of 4 gates gives a positive result if window 1 or window 2 triggers, and so on for the other gates. But then what we can do is combine them into OR gates and further into other OR gates until finally we get to the point where the output Y is positive if any of those sensors are triggered. And we've talked a bit about the truth tables, but we haven't really looked at them as combinations before. Here's an interesting truth table. We can see that in the case when window 1 is triggered, even if all of the other sensors are not triggered, our alarm triggers. If window 2 triggers, regardless of the other sensors, the alarm triggers, and so on and so on and so on until we get down to the opposite case where notice none of the sensors are triggering, and so the alarm does not go off. Now there's something interesting to note here. This is not a complete truth table. Why not? Pause the video for a second and see if you can figure out why this is not a complete truth table. Okay, hopefully you worked out the answer. The answer is we could have more than one sensor triggering on. And so there are in fact many, many more potential combinations for our circuit that we haven't considered here. But we know from what we've looked at that the results would be redundant if, for example, window 4 and window 5 trigger. Well, since it's an OR gate, we're still going to see the alarm trigger, which is the result we want. Now, there's a small problem with our alarm system. So you might want to pause the video again for just a second and think about what's the issue with the circuit that we've designed for our alarm system. And the answer is that we can't get into or out of our house without triggering the alarm. There's no way to disable it. So we need a little bit more elaborate logic if we want to have a practical burglar alarm system. What we can do is in simple word terms, we can state that a sensor must trigger and the system must be enabled in order to have the alarm go off. And notice that it's pretty easy to decide what kind of gate we want to add here. We need an AND gate. So if we incorporate the existing circuit that we designed and add to it now an AND gate, we can see that in this case we need one of the sensors to trigger and the system must be enabled in order to have the gate provide voltage to the alarm switch, the Y output. And our truth table will look something like this. So now it becomes much more elaborate because we have to consider the logic of whether the alarm is enabled. Notice again, this is our truncated truth table. There's still many possibilities we've ignored because they reproduce the same result. So we can see that in any case, no matter what happens with our sensors, if our system's not enabled, the alarm doesn't go off. Good, we can get into our house. However, if the alarm's enabled, the only case we need is one of the sensors to trigger and the alarm goes off. So our new Boolean expression then becomes y equals all of the sensor inputs in OR form and the alarm enabled. So there's a practical application of the logic gate concept. Okay, to summarize, logic gates are the basis of modern electronic logic. They're based on Boolean algebra, and we can combine logic gates with other gates and create circuits that produce the outputs we want from given inputs. We represent the behavior of these gates or combinations of gates using truth tables. So now I'd invite you to spend some time and complete the worksheet using the logic gate simulator that I showed earlier in the lesson. I'd like you to hand that in tomorrow morning, but also please review the handout for the activity for tomorrow. There will be a fair number of wires to wire up tomorrow, and if you're not well organized, you're probably going to run out of time. So you'll want to review that before you get in tomorrow. Again, here's the hyperlink for the logic lab that we saw. Have a wonderful night.